Good day. The topic today is the study of inverse functions and their derivatives. And let's first just review a little bit of what you would have learned in algebra or pre-calculus about inverse functions and how they are related. This graph is showing the function y equals x squared plus 3 and the function y equals the square root of x minus 3. And let's just show that they are inverses of each other. That what that means is if I take a number x and I evaluate the first function, let's take the value x equals 1 and I plug it into the red function x squared plus 3, I'm going to get the y value 4. So if this was f of x, f of 1 would be 4. Now if I take that number 4 and plug that into the other function, I'm going to get the square root of 4 minus 3, which is back to 1. So if we were to call this function f of x, and we were to call the blue one g of x, what we're noticing here is that if I did g of f of x, and I got back to my original x. For example, when I started with x equals 1, f of 1 was 4, but then when I did g of 4, I got back to 1. And it also works in reverse. If I started with 4 in g and got g of 4, I get 1. And then I take that 1 and plug it into f, I get back to 4. So it also works this way. F of g of x also gets me back to my original x. And what this means is that we can call g the inverse of f and use this notation right here. Okay, so in this context, this raised minus 1 is the notation for the inverse of the function. And today we're going to study the derivatives of the inverses of functions. So in this picture here, what that would mean is we're going to be studying the relationship between, let's say, the slope of the tangent line at this point 1, 4 on f of x. And how does that relate to the slope of its inverted point on g of x, which would be the point 4, 1? Okay, so the lesson today is about how does the derivatives or slopes of those 2 points relate? And I can see here that things like, well, they're not the exact same. The slope here does not seem to be as steep as this one. And if I were to move to a different point, like this point here has a very steep slope, but its corresponding point on the other function is over here, and it's much flatter. Okay, so they're not quite the same. And what I intend to do in this lesson is to prove to you what the relationship is and then apply that rule so that even in the case where I don't know what the inverse function is, if I just know a function and I want to find the derivative of its inverse, I can use this rule instead of having to go hunting for the inverse function. Because in this case, really, I know the explicit formula for g of x. I could just differentiate this and find the slope of all these points. But the fact is, lots of functions have an inverse that is difficult to find algebraically. So I would want to know the relationship or this theorem that we're going to learn today. So I would not need to know the explicit formula for the inverse function necessarily. So on this slide here, we're going to prove to you what the relationship is. So I'm going to again use the function names f of x for supposedly our like original function, and then g of x will denote its inverse of f of x. So even though we're not going to use the symbol f inverse, we need to realize that. And so I'm going to make a note of that here, that g of x is just another name for f inverse of x. And we're going to start with writing that property that if I form a composition of a function and its inverse function, we always get back to the original x. We saw that in the last slide where I had g of 1 was 4, but then f of 4 was back to 1. Okay, and if that works every time, that really means the functions are inverses. So we're going to presume then that f and g are inverses, and therefore f of g of x is equal to x. That's a property of inverse functions. But now we're going to take the derivative of this equation. So I've applied the derivative symbol to both sides. And on the right side, that's a standard, we know the derivative of x is 1. And on the left side, we know how to differentiate this composition because we've learned the chain rule. So the chain rule applied to f of g of x, this is exactly how we wrote the rule, is f prime of g of x multiplied by g prime of x. But the purpose of this process is we want to find the derivative of that inverse function. We want to find g prime of x, which would also be called f inverse prime of x. Okay, we're just going to call it g prime here, or g relation to g, so these are easier to write. So I'm going to solve for g prime by dividing by this expression f prime of g of x. So by doing that, I've got the expression g prime of x is 1 over f prime of g of x. And essentially what this is saying, if I go back to the graph that we had a minute ago, is that what this essentially is saying is that if I want to find the slope on an inverse of a function, let's say the point 4,1 on the inverse function, what we just proved was that slope is in fact the reciprocal of what the slope is at this other point that it came from, the point 1,4 in this case. So presumably we would know the expression for the original f function, like x squared plus 3, and I could easily find the slope using a standard derivative at the point 1,4. And all I have to realize then is that what I just proved, and that is the slope at the point 4,1 on the inverse is going to be the reciprocal of the slope of this point. So if I can almost do this in my head here, at the point 1,4, where x is 1, the derivative of x squared plus 3 is 2x, and so f prime of 1 is going to be 2 over 1. And what that means is, without doing anything else, I just proved that the slope of this point over here is going to be 1/2, the reciprocal of 2. Those two slopes are reciprocals of each other. Okay? As we're filling in our list of differentiation rules, this is the way we wrote it. This is the way I have it set up on there for you to write down. On the back of your purple sheet, number 6, we were going to write that the derivative of the inverse of a function is the reciprocal 1 over the derivative of f at the inverse of x. Essentially what that is saying again is that the slope of a point on the function f of x compared to the slope of its corresponding inverted point on the inverse function, those slopes are reciprocals of each other. Okay, so the next couple of minutes here, we're going to take a look at some examples where I'm giving you the function f of x, but we're asked to find the slope of g of x, the inverse function, and using this relationship here. Okay, so the question we're asked is find the slope. Oh, sorry, I'm getting ahead here. It says find the derivative of the inverse of f. Okay, so if I'm given the function f of x, we're asked to find f inverse of a number a. So we're always given the number a. And I'm going to make a note in the middle here what the rule was again. Our theorem was that the derivative of the inverse function is the reciprocal of the slope of the original function evaluated at the f inverse function of a. So the first thing I always do is figure out what this number is going to be right here. Okay, and usually this is just either guess and check, or just making an observation, or we actually, if all else fails, we write it down as an equation. So if I want to know what is f inverse of 8, if I don't know that, what I want to ask, I could also ask in a different way and saying f of that number would have to be 8. And in this case, that's just one we can observe here, that if the function is x cubed, we can just do that by either guess and check or just by observation, that x cubed, or that if x cubed equals 8, means that x is 2. Which means I can go up here to my original question and say, well, since f of 2 is 8, f inverse of 8 is 2. And now I'm gonna need that now in my little rule. That essentially what this theorem says now is if I can find the slope of f of x at 2, the slope I want is the reciprocal of that. Okay, so I'm going to go find f prime of 2 actually first, by first finding f prime of x, and this time that's an easy one. That's 3x squared. And I'm now going to find f prime of 2, which is going to be 3 times 2 squared, which is 12. And so now all I'm going to say is the f inverse prime of 8 is 1 over 12, because it's the reciprocal of the slope of f at 2. Okay, so to summarize what we've just discovered here, there's two functions mentioned in this problem, f of x and f inverse of x. Okay, the function f of x contains the point 2, 8, and the slope there was 12. The inverse function contains the point 8, 2, and with just knowing the theorem here, the slope at this point has to be the reciprocal 1/12. So this, I always kind of just write my conclusion here, and just helps me kind of solidify what I'm learning in the theorem here. That what I was really asked for was the derivative of the inverse function at 8. And what I did was, the theorem says find the inverse point, the point 2, 8, on the function f of x, find its slope using a traditional derivative and plugging in this case 2, and then the slope that I really want is just going to be the reciprocal of that answer. So what I really was going for was this over here. Okay, so our other example today is this one. The function is going to be x cubed plus 2, and I'm asked for the derivative of the inverse when x is 12. So what we want here is the derivative of the inverse function at 12. Okay, so actually, let's just make a note of that previous way I've summarized our work here. There's the function f of x, and there's the function f inverse of x. Now, we are tasked with finding the slope on f inverse when the x is 12. Now, I don't know the rule for the f inverse function, so I don't know what this point is yet. But on the original function, then, that means there's a point where the y coordinate is 12. And so I could find my missing number by thinking about it that way. What number, when plugged into the original function f of x, would get me the y value 12? And that would give me the f inverse of 12. Well, let's just do this by kind of guessing and checking, or just by observation again. 1 cubed plus 2 times 1 does not make 12. However, if I try 2, 2 cubed plus 2 times 2 is 8 plus 4, and that makes 12. So I can just tell by a few guess and check attempts that f inverse of 12 is 2. Okay, and now the theorem says if I want to know the slope here, what I'm really going to do is find the slope on f of x at the point 2, 12, and then all I got to do is flip it upside down over here. So my work is really to find f prime of 2 and then once I find that answer, that slope is going to be reciprocal over here. Okay, so the derivative of x cubed plus 2x is 3x squared plus 2, And now the inserted number is going to be 2. And so I get all told here, this is 14. And so the slope of f at the point 212 is 14, and that makes the slope here, the one I was asked for, 1/14. And so that's my conclusion. F inverse prime of 12 is 1/14. Okay, I hope this helps you with some of the exercises that are on your assignment sheet. The next video will be outlining how we apply this principle specifically to the trigonometric functions.